The Big Bang. In Friedman's first model of the universe, the fourth dimension time, like space, is finite in extent. It is like a line with two ends or boundary. So time has an end and it also has a beginning. In fact, all solutions to Einstein equation in which the universe has an amount of matter we observe share one important feature. At some time in the past, about 13.7 billion years ago, the distance between neighboring galaxies must have been zero. In other words, the entire universe was squeezed into a single point with zero size, like a sphere of radius zero. At that time, the density of the universe and the curvature of the space-time would have been infinite. It is a time that we call the Big Bang. All our theories of cosmology are formulated on the assumption that space-time is smooth and nearly flat. That means that our all theories break down at the Big Bang. A space-time with infinite or unmeasurable curvatures can hardly be called nearly flat. Thus, even if they are events before the Big Bang, we cannot use them to determine what would happen afterward because predictably would have broken down at the Big Bang. Correspondingly, if as is the case, we know only what has happened. Since the Big Bang, we cannot determine or just cannot find what happens forward. As far as we are concerned, events before the Big Bang can have no consequences and so should not form a part of a scientific model of the universe. We should therefore cut them out of the model and say that the Big Bang was the beginning of time. This means that questions such as who set the condition for the Big Bang are not questions that science addresses. Another infinity that arises if the universe has zero size is in temperature. At the Big Bang itself, the universe is thought to have been infinitely hot. As the universe expanding, the temperature of the radiation decreases. Since temperature is simply a measure of average energy or speed of particles, this cooling of the universe would have a major effect on the matter in it. At very high temperature, particles would have moving around so fast that they could not escape any attractive force or just attraction between the particles, and now each other resulting from nuclear or electromagnetic forces. But as they were cooled off, we could accept particles that attract each other to start to clump together. Even the types of particles that exist in a universe depend on a temperature and hence on the age of the universe. Aristotle did not believe that matter was made of particles. He believed that matter was continuous. That is, according to him, a piece of matter could be divided into smaller and smaller bits without any limit. There could never be a grains of matter that could not be further divided. A few Greeks, however, such as Democritus, held that matter was inherently grainy and that everything was made up of large numbers of various different types of atoms. The word atoms means individual in Greek. We know that this is true at least in our environment and in the present state of our universe, but the atom of our universe does not always exist. They are not invisible and they represent only a small fraction of the type of particles in the universe. Atoms are made up of smaller particles, electrons, protons, and neutrons. The protons and neutrons themselves are made up of yet smaller particles called quarks. In addition, correspondingly to each of these subatomic particles, there exists an antiparticle. Antiparticles have the same mass as their sibling particles but are opposite in their charge and other attributes, and also have different behavior. For instance, the antiparticle for the electron, called a positron, has a positive charge, the opposite of the charge of the electron. There would be both antiwords and antipeople made up of antiparticles. However, when an antiparticle and particle meet, they inherit each other. So, if you meet your nth step, or just like same as you, don't shake your hands. You would both vanish in a great flash of light. Light energy comes in a form of another types of particles, a massless particle called a photon. The nearby nuclear furnace of the Sun is the greatest source of photons for the Earth. The Sun is also a huge source of another kind of particles, a four-mentioned neutron called antineutron, but these extremely light particles hardly even interact with matters, and as they pass through us without effect at a great rate of billions each second. All told, physicists have discovered dozens of these elementary particles over time. As the universe law undergoes a complex evolution, the makeup of this zoo of particles has also evolved. It is the evolution that has made it possible for planets such as Earth and beings such as we to exist. 1 second after the universe, 1 second after the Big Bang, the universe would have expanded enough to bring its temperature down to about 10 billion degrees Celsius. This is about 1,000 times the temperature at the center of the Sun, but temperature as high as they reach in hydrogen bonding explosions. At this time, the universe would have contained mostly photons, electrons, and neutrons, and their antiparticles together with some protons, and neutrons. These particles would have had so much energy that when they collide, they would have produced many different particles, antiparticles pair. For instance, colliding photons might produce an electron and its antiparticle, the positron. Some of these newly produced particles would collide with the antiparticle siblings and be annihilated. Any time an electron meets with its positron, both will be annihilated, but the reverse process is not so easy. In order for two massless particles such as photons to create a particles or antiparticles pair, such as the electron and a positron, the colliding mass is less. Particles must have a certain minimum energy. This is because an electron and a positron have mass, that is 9.1 into 10 to the power minus 31 kg, and this nearly creates mass but come from the energy of the colliding particles. As the universe continued to expand and the temperature to drop, collision having enough energy to create the electron-positron pair would occur less often than the rate at which the pairs were being destroyed by annihilation. So even eventually, most of the electrons and positrons would have inherited each other to produce more photons, and leaving only relatively few electrons. The neutron and the antineutrons, on the other hand, interact with themselves and with other particles only very weakly, so they would not inherit each other nearly as quickly. They should still be around today. If we could observe them, it would provide a good test of this picture of the very hot early stage of the universe, but unfortunately, after billions of years, their energy would now be too low for us to observe them directly. Thought we might be able to detect them indirectly about 100 seconds after the Big Bang. The temperature of the universe would have fallen to 1 degree or 1 billion degree. The temperature inside the hottest star at this temperature, a force called a strong force, would have played an important role. The strong force will be now is a short-range attractive force, that is strong nuclear force, that can cause protons and neutrons to bind to each other, forming nuclei. At high enough temperature, protons and neutrons have enough energy of motion, and that can emerge from their collision is still free and independent. But at 1 degree degrees, there would no longer have been sufficient energy to overcome the attraction of the strong force, and they would have started to combine to produce the nucleus of atoms of deuterons, that is heavy hydrogen isotope, which contains one proton and one neutron. The deuterium nuclei would have then have combined with more protons and neutrons to make helium nuclei, which contain two protons and two neutrons. Also, small amounts of a couple of heavier elements, lithium and barium. One can calculate that in a hot Big Bang model, about a quarter of the protons and neutrons would have been converted into helium nuclei, along with a small amount of heavy hydrogen and other elements. The remaining neutron would have decayed or just destroyed into photons, which are the nucleus of an already hydrogen atoms. The picture of a hot early stage of a universe was first put forward by the scientist George M. Gamow in a famous paper written in 1948 with a student of his, Ralph Alpert. Gamow has quite a sense of humor. He persuaded the nuclear scientist Hans Bethe to add his name to the paper to make the list of authors Alpert, Bethe, and Gamow, like the first letter of the Greek, alpha, beta, and gamma, and particularly approach for a paper on the beginning of a universe. In this paper, they made a remarkable prediction that radiation from a very hot early stage of a universe should still be around today, but with its temperature reduced only a few degrees, about absolute zero, that is 273 Celsius, is the temperature at which substance contains no heat energy and is thus the lowest possible temperature. It was a microwave radiation that Penzias and Wilson found in 1965. At the time that Alpert, Bethe, and Gamow wrote their letter on paper, not much was known about the nuclear reaction of protons and neutrons. Predictions made for the propagation of various elements in the earlier universe were therefore rather inaccurate. But these calculations have been replaced at the light of better knowledge and now agree very well with what we observe. It is moreover very difficult to explain in any other way why about 1/4 of the mass of the universe is in a form of helium. But there is a problem with this picture. In a hot Big Bang model, there are not enough time in the early universe for heat to have flowed from one region to another. This means that the initial stage of a universe would have to have exactly the same temperature everywhere in order to account for the fact that a microwave background has the same temperature in every direction we look. Moreover, the initial rate of expansion would have to be chosen very precisely, for the rate of expansion is so close to the critical rate needed to avoid collapse. It would be very difficult to explain why the universe should have begun in just this way, except as an act of a God who intends to create beings like us, in an attempt to find a model of the universe in which many different initial configurations have been evolved to something like the present universe. A scientist at the Macarthur Institute of Technology, Alan Guth, suggested that the early universe might have gone through a period of very rapid expansion. This expansion is said to be infinitely, meaning that the universe at one time expanded at an increasing rate. According to Guth, the radius of a universe increased by the million, one with 30 zeros after it, times in only a tiny fraction of the second. Any irregularities in a universe would have been smoothed out by this expansion, just as the wrinkles in a balloon are smoothed away when you blow it up. In this way, inflection explain how the precision or how the present smooth and uniform state of a universe could have evolved from many different non-uniform initial states. So we are therefore fairly confident that we have the right picture, at least going back to about 1 billion trillions of seconds after Big Bang. After all the initial turmoil, within only a few hours of the Big Bang, the production of helium and some other elements such as lithium would have stopped. And after that, for the next millions years or so, the universe would have continued expanding without anything much happening. Eventually, once the temperature had dropped to a few thousand degrees, and electrons and nucleus no longer had enough energy of motion to overcome the electromagnetic attraction between them, they would start combining to form atoms. The universe as a whole would have continued expanding and cooling, but in this region they are slightly denser than average. This expansion would have been slowed down by the extra gravitational attraction. This attraction would eventually stop expanding in some other regions and cause them to start to collapse. As they are collapsing, the gravitational pull of matter outside this region might start then rotating slightly. As the collapsing region got smaller, it would spread faster, just a scatter spinning on a escape, faster as they draw in their arms. Eventually, when the region got small enough, it would be spinning fast enough to balance the attraction of gravity, And in this way, disk-like rotating galaxies are born. Other region that did not happen to pick up a rotation would become obvious because called elliptical galaxies. In this, the region would stop collapsing because invisible parts of the galaxy would have orbiting stably around its center, but the galaxy would have no overall rotation. As time went on, the hydrogen and helium gas in a galaxy would break up into the smaller cloud that would collapse under the own gravity. As they are contacted and atoms within them collide with one another, the temperature of the gas would increase until eventually it becomes hot enough to start nuclear fusion reaction. This would convert the hydrogen into more helium. The heat released in this reaction, which is like a controlled hydrogen bomb explosion, is what make a star shine. This addition heat also increases the pressure of a gas until it is sufficient to balance the gravitational attraction, and the gas stops contracting. In this manner, these clouds collapse into stars like our sun, burning hydrogen into helium and radiating the resulting energy as heat and light. It is about like a balloon. There is a balance between the pressure of air inside, which is trying to make the balloon expanding, and the tension in the rubber, which is trying to make the balloon smaller. Once cloud of hot gas collides into star, the star will remain stable for a long time with heat from the nuclear reactions, balancing the gravitational attraction. Eventually, however, the sun will run out of its hydrogen and other nucleus and fuels. Paradoxically, the more fuel a star starts off with, the sooner it's run out. This is because the more massive the star is, the hotter it needs to be balance its gravitational attraction, and the hotter the star, the faster the nuclear fusion reaction, and the sooner it will use its fuel. Our sun has probably got enough fuel to last another 5 billion years or so, but more massive stars can use up their fuels in as little as 100 million years, much less than the age of a universe. When a star runs out of a fuel, it starts to cool off, and a gravity takes over and causes it to contract. The contraction squeezes the atom into thus together and just cause the types of stars to bend down, and the cause this star to become hotter again. As the star heats up further, it would start to convert helium into heavier elements such as carbon or oxygen. This, however, would not release much more energy, so to crisis would occur. What happened next is not completely clear, but it seems likely that the center region of a star would collapse to a very dense state such as black hole. The term black hole is very recently originated. It was coined in 1969 by the American scientist John Wheeler as a graphic description of an idea that goes back at least 200 years to a time when there is no theories about lights. One which Newton favored was that it was composed of particles, and the other was that it was made of waves. We know that earlier both theories are correct, as by the waves or particle duality of the quantum mechanics, light can be regarded as both as a wave and a particle. The descriptor waves and particles are concerned human created, not necessarily concept that nature is obliged to result by making all phenomena fall into one category or the other.